All right. I can turn on the projector. Dang, look at that. I'll gladly try to do that. All right, so if you will, get your bridge assignments out. If they were all atrociously wrong, it's fine. If they were all perfect, I'm glad. But for today, because there's so many different kinds of, it's the same like 3 reactions. There's a lot of different ways to ask these questions. I wanted to make kind of as complicated questions as I could and have us go through these kind of as examples really of just what a quiz question might look like. I'm trying to make things as challenging as possible when we go through them. So before we go through this, did you have any questions in general about nucleophilic aromatic substitution or Friedel-Crafts acylation? I'm hoping that based on alkylation, acylation seemed a little bit more simple in comparison. So nucleophilic aromatic substitution. It's different. It's the first new reaction we've done in like 2 weeks. You need a nucleophile, you need a leaving group. So it's a lot more like SN2. You need an aromatic ring. What's the 4th thing you need in addition to that? I'll give you an example. Here's the problem right here. This is nucleophilic aromatic substitution. Okay, so we do need heat. So there's a kind of a 4th thing that you need. So you need a leaving group. Here we got a leaving group. Fluorine, good news. Fluorine gets to be a leaving group for nucleophilic aromatic substitution. It has never been a good leaving group before for SN2. So fluorine gets its time in the sun, finally. There's fluorine. You need an aromatic ring. Here's a nucleophile. This is an O-. So you got a nucleophilic, aromatic, you got a leaving group for substitution. But if you want to do this at reflux, which is around 100 degrees, what else do you need? Yes, where? Yes, this is really important. You need an electron withdrawing group, which is one of those deactivating groups, either ortho or para to the spot where you do substitution. If you don't have that, you'll have to heat it up to 350 degrees. Let's have a public service announcement about 350 degrees. How hot's that? We're talking Celsius, by the way. So I know that your ovens go up to 350 degrees at home, but that's Fahrenheit. 350 degrees Celsius is super hot. It is hotter than your ovens go. How high can we heat water? 100 degrees. How high can we heat ethanol? You might not know this, like 70 some degrees. Sometimes we will use ethylene glycol when we need a really high heat reaction. That goes up to 200 degrees. 350 degrees is ridiculous. You basically have to set up some type of sealed bomb, kind of like a pressure cooker, in order to get a reaction that hot. So that's the one that goes through that really weird Benzyne intermediate. We're never gonna do that. We're in fact gonna not do that reaction at all. I'm not gonna ask you about it because it is ridiculous. I do want you to know that it is possible to do nucleophilic aromatic substitution without a leaving group, ortho or para. But for all practical purposes, it's not going to happen unless you have a leaving group, ortho or para. That makes sense? So that's a thing that can be done under ridiculous circumstances. We are never going to do those ridiculous circumstances. So you need 4 things for nucleophilic aromatic substitution. Nucleophilic, aromatic. And the substitution has a leaving group usually, so you need a leaving group. And then the 4th thing is you need to have some type of electron withdrawing group, which happen to be those deactivating groups for electrophilic aromatic substitution. And you need them ortho or para. All right. So any other questions about those reactions? Otherwise, I'm just going to start calling on you guys to go through these problems, and we're going to go through them all together, and we're all going to get to the right answers, whether or not we have them written down at this moment. Okay, so Mackenzie Kelly, would you like to start us off today? Great, thank you very much. So this is an alkyl chloride and AlCl3. So this is one that we did on Friday. All right, so this would be Friedel-Crafts alkylation, whether or not you remember that term. So tell me what this is going to become. It is. So aluminum chloride serves to make the chlorine a better leaving group. So chlorine hooks up to that and then it leaves. So that would give us something like this question mark. Okay, close, but this has a problem. So this is a primary carbocation. And a big part of what we did on Friday is that what happens to primary carbocations if they can? It's one of the major issues with Friedel-Crafts alkylation. You remember? Anybody remember what happens to that? It's gonna rearrange, right? So anytime, this is super important. Anytime you have a primary carbocation for Friedel-Crafts alkylation, it'll rearrange if it can, have anywhere better to go. And so because this is primary and its neighbor is secondary, you won't actually get any of that. You will get this one instead. So therefore, this is going to be your electrophile. And that's what's going to substitute onto the ring. And so you're going to have a benzene ring. And what do we take off? The electrophilic aromatic substitution. Exactly. And we replace it with this chunk right here. All right. So I did go through and look at all of these bridge assignments. And we were about 50-50 on 1A. But this is what is going to happen. So make sure that when you do Friedel-Crafts alkylation, that you draw out the product and see if it can rearrange. And if it will, then it can. And that rearranged version is what you put on. If you're unclear on that, ask me questions or go back to Friday's class because we spent a lot of time doing that on Friday. All right, Gabe, talk to me about this first step here. What's this thing? Yep. It's an acid chloride or an acyl chloride. Yep. Yep. Sure. Yep.
And it will be alkane chain of Eldorado.
Yep. All right, pause. Yes. Hold on. Wait. Okay. This is do the first step of the first step. All right. So after that's the first step, you're absolutely right. So this is Friedel-Crafts acylation, which is a whole lot like alkylation. Do you have to worry about rearrangement for acylation? No, you do not have to worry about Friedel-Crafts acylation ever rearranging. You just straight up slap that thing onto the benzene ring and you're done. At least for our step one. But the aluminum chloride does the same thing. It makes the chlorine a good leaving group, as Gabe pointed out, and then you kind of get that plus charge right here. For alkylation with an alkyl group, worry about the possibility of rearrangement. For the acyl group, don't worry about the possibility of rearrangement. All right, so that would be the end of step one. And then in step two, this is an oldie, like we did like 2 or 3 weeks ago. Yep. So this is one of the complete reduction reagents. This is for the Clemmensen reduction. You can do it with Wolff-Kishner instead, which was the NH2 followed by KOH and heat. But in that second step, you are just turning it into an alkane. So putting these two reactions together, that's a little sloppy, but hopefully you can see what's going on here. This is how we're able to make a 4-carbon chain directly attached onto a benzene ring at the primary carbon. So we could not make this thing through Friedel-Crafts alkylation because of rearrangement, but we can through acylation followed by reduction. So acylation followed by reduction is always going to give you a CH2 followed by a bunch of stuff. So it's always going to be kind of a straight chain coming off of there. And alkylation is pretty much never going to give you a straight chain coming off of there. So you get completely different reagents for those two different ways of approaching. All right, questions on that one? All right, Natalie, go. Yep. Yep.
And then that chunk gets added.
Correct. So that chunk gets added on here. Boop, 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 boop.
And then that chunk is meta. ACL.
Perfect. So this part right here, because your first carbon is a carbonyl, this is meta directing or electrophilic aromatic substitution. And that's what we're doing in the second step here. So a lot of what we did in the previous outcome with electrophilic aromatic substitution is still going to be important for this one. So all of these things are going to go hand in hand. So that will put a chlorine on, as you said, meta to this. So we would have All right, if you haven't started on it yet, this bridge assignment and a lot of these questions are very, very similar to your first 2 pages of retrosynthesis 3. All right, so I would recommend that you start on that soon. It's probably going to give you a good way to study for this Wednesday's quiz. Because it's the same types of reactions, just over and over again. All right, good, 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 good. Colette, step one. Great. All right, step two. Okay, so let's remind ourselves about the issues and limitations with Friedel-Crafts alkylation and acylation. What was number one? So it's the reaction won't work if it has what on the ring already? Yeah, oh, well, close, a deactivating group. So the deactivating groups were all of the meta-directing ones and the halogens. So
then it won't go any farther from there.
exactly, perfect. So Friedel-Crafts alkylation and acylation had slightly different limitations, but the one that they had in common is that neither one will work if you have a deactivating group on the ring already. And the deactivating groups are the meta-directing ones, so like carbonyls or plus charges, partial plus charges, or halogens. Because halogens are strongly electronegative, they pull electrons away from the ring, which means that this ring is not going to be electron rich enough to share with a C+. Or to say it the other way, a C+ is not reactive enough to react with one of those rings. So, yes.
So then why in the problem above, it continues to go when the C11O is a partial charge?
Good question.
Because I had them switched, I had the one above it saying it didn't
Okay.
go farther, and then that one did.
So if you have a deactivating group on the ring, Friedel-Crafts alkylation and acylation won't work. If you have a deactivating group on the ring, chlorination is fine. Nitration is fine. Sulfonation is fine. Iodination is fine. They're just meta-directed.
So if there was a carbon chain attached to that chlorine, and it was, then that wouldn't have worked for the problem above. Do you like
Yes.
if it, for step one was the acylation, and then step two, instead of Cl2, it was Cl with an ethyl group on it, the reaction would not have gone further?
Correct. Good. Yes. So good point. So if my first step put on a deactivating group, and for a second step, you try to do more alkylation, Friedel-Crafts alkylation or acylation, it wouldn't work. So those reactions from last week, those 5 reactions we had, they will work. They don't have the same limitations that the Friedel-Crafts ones do. They'll work just fine with a deactivating group on there. That's how we got meta-directed stuff. So this is not a new rule that applies to the old stuff. It's a new rule that just applies to the Friedel-Crafts reactions. So in this one, we did the Friedel-Crafts thing first, followed by chlorination. And so chlorination was fine, it just went meta. Here we did chlorination first, so we put on a deactivating group. But then this reaction wouldn't work, because one of the major limitations of the Friedel-Crafts alkylation or acylation, it wouldn't work if we used like, none of these previous reactions would work if you had a chlorine on the ring, or a nitro group, or a carbonyl, or anything like that. So for that second step, there's just no further reaction. So basically, this thing won't work with chlorine on the ring. So this was a pretty tricky question, and I wasn't trying to make you guys fall for something and get it wrong, but it's really important to remember that, especially when we get into how to do this kind of thing in reverse. Because in reverse, it's worth noting that if you want to put on multiple different groups, your Friedel-Crafts alkylation generally doesn't go on last, because most of our other reactions put on deactivating meta-directing groups. All right. Questions on that one? Does that make sense? All right. All right, Deanna, what do we got? Yep. Good. So we get rid of that sodium, right? And that O becomes what charge? Negative. Perfect. So this is a strong nucleophile. And Where on this ring will it attach? Where your leaving group is. Perfect. All right. Important. All of these other reactions, the electrophilic aromatic substitutions that we did with Friedel-Crafts acylation for today and all of the other things from the previous 2 weeks, they put on electrophile and you take off a hydrogen. With a benzene ring, you usually have lots of hydrogens. And so that's why we had this idea of ortho-directing, para-directing, meta-directing, because there were usually a lot of different places where it could possibly happen. For a nucleophilic aromatic substitution where you're adding a nucleophile, you don't have a choice. It must happen where there's a leaving. So you don't have to worry about, with nucleophilic aromatic substitution, trying to figure out where this reaction is going to happen so much. It's always going to happen at the spot with a leaving group. And if there's multiple leaving groups, it'll either happen at both, but it has to have that, just like you mentioned, that electron withdrawing group, ortho or para. All right, so yes, our 4 different things. We've got a nucleophile, we got an aromatic ring, we got a leaving group. What was the 4th thing? Yeah, that electron withdrawing group, that nitro, and it's para to the spot with a leaving group. So what are we going to do? Yep. Perfect. So we're going to add on this chunk and remove fluorine. OCH2CH3. Do remember, this is something we did a lot with SN2. It's not going to attach one of the carbons. It's going to attach whatever has the negative charge. That's the nucleophile. That's the part that attaches. All right. Mackenzie, you ready? Okay. So sodium hydroxide splits up into Na plus and what? Great. And OH minus is a strong nucleophile. So we're going to go through our 4 things. Do we have a strong nucleophile? Do we have an aromatic ring? Do we have a leaving group? Do we have an electron withdrawing group, ortho and or para to the leaving group? No. So will this reaction work? No. This reaction would work if we heated it up to 350 degrees, but refluxing it in water is not going to be 350 degrees. So is this reaction going to do anything? No. So you can say that was a trick question if you want to, but here are the qualifications. It's still those 4 things. And if you don't satisfy them, it's not going to work. All right, I'm going to slip in here another question. Sorry, Gabe, you get a bonus question you haven't tried before. All right. I've got 2 different leaving groups. So where do you think you're most likely to do this reaction? Which one is that? So this one right here. Right. So chlorines are electron withdrawing groups. So technically both of these have an electron withdrawing group, ortho, because they're right next to each other. That make sense? So feasibly, either one could possibly work. But this chlorine right here as a leaving group has an electron withdrawing group, both para and ortho. So it would be much better for nucleophilic aromatic substitution. So it's possible that you could get this one, but because this would happen way faster, that's where you're going to do your substitution. So this one has electron withdrawing group, ortho and para. And so therefore, that's where you'd be more likely to do this. So if you have multiple leaving groups, you have to think about really that rule, which is that 4th thing you're looking for, electron withdrawing groups, ortho and or para. So that's what we would do. Good job. All right, questions on that one? That makes sense? We're looking for that 4th thing. So it always has to be at one of the spots with the leaving group, but this one right here has an electron withdrawing group, ortho and para, which is better than that one, which only has an electron withdrawing group, ortho and meta, but meta is useless. All right, so that's kind of how we do these forward. Some of them were multi-steps. You should probably expect that. You should do the homework problems, but if you got all of those correct, good job. I went through this homework and I don't think everybody got everything correct, which is absolutely okay. All right, Natalie, are you ready? All right, so what have we done? Sure. So how you want to make this happen?
Yeah.
Sure. Would you like the chlorine to be attached to carbon number 1 or to carbon number 2? 1. Sure. Okay. So we are attaching this 4-carbon chunk. Probably what I would recommend is the easiest way to do it. By the way, hold on, because you're correct as well. Is I would imagine that for the sake of your thought process, this is the carbon that we're attaching. So probably the easiest way to think about that is just do the same thing with a chlorine attached to that carbon. And that would work just fine. However, because of rearrangement, if you had a 4-carbon chain with the chlorine at the very end, and you added aluminum chloride, it looks like we would get this, but that thing would rearrange to become this, which would be a 4-carbon chunk with the plus charge on carbon number 2 anyway. So it would work wherever you put the chlorine in this case. That's not always true. So probably the best thing to do, or at least you optimize your chance of getting it right if you don't remember every rule, is to just have whatever chunk is attached with a chlorine attached at wherever your new bond is. So this would work, or that. So either one of those with aluminum chloride would be just fine. That makes sense. Everybody good with that? All right, Colette, what about this chunk here? Correct. So this is really important. A lot of people did alkylation again, but as we just saw here, Natalie modeled this for us, that if you use the 4-carbon chunk with chlorine on carbon number 1, it will rearrange and you will not get this. So if you ever want to have a straight chain that's more than 2 carbons, it's gonna rearrange. So yes, you have to do acylation first. So what should we add? Yeah. Yeah, so 4 total carbons, just like we have 4 total carbons. Uh-huh.
And then you'll add the zinc mercury HCl.
Yes. So this is, we need to then do a full reduction, and you can use Clemmensen reduction or Wolff-Kishner, either one. This is usually the one that gets done. It's only 1 step and it's pretty cheap and easy. So that would work, and that would, so essentially what we're doing is first, we're attaching this as an acyl group, and then second step, we're chopping off the carbonyl and just leaving us with an alkyl. So acylation and reduction is a very common combo. If you just want to have the acyl group, just use the acyl. That'll give you a ketone. But if you want to turn it into an alkane afterwards, that's a straight long chain, you do acylation and reduction. So this pair, this combo, is going to be pretty consistently something that you'll see in aromatic ring reactions. All right, questions on that one? Okay, Deanna, you ready? All right, you got 2 different things going on here. Yes, so she just said you have to attach your isopropyl. Tell me why we need to attach our isopropyl first. Yes, the chlorine is deactivating. So if you put the chlorine on first, it would technically be para-directing, but putting on an alkyl group won't work if there's a deactivating group on there already. Great, great. So how do you attach this thing? Okay. Then, perfect. Okay, so the order matters. Order is important. It won't work if you go the other way around. That is just right. Any questions on that one, anybody?
What is standard 3-carbon chain?
Yep. So if you did it this way, oh, that's 4, sorry. 1, 2, 3. This is your step 1. Either one of those would work. You could do isopropyl chloride or propyl chloride. Either one would be fine. All right, How are we feeling? You can do this? All right. Good news. It's getting bigger and bigger. Are you ready, Mackenzie? Okay.
So first we H and then we can speak to that.
All right, so let's play this out. So HNO3 and H2SO4 would attach what to your ring? Okay, so that would put on the NO2. All right, so that is true. Then what?
And then the CN attached to the
Okay, so unfortunately, if you put on the nitro first and then you tried to add all of this, you got multiple problems. First and foremost, Friedel-Crafts alkylation and acylation will not work if there's a deactivating group on there already. And this is a deactivating group. Furthermore, do you remember how nitro directs a second substituent? It is, so it's meta directing. So if you could put on something second, it would appear meta instead. All right, so that's okay. So that won't work. And a lot of what you're going to do for this kind of thing is try stuff and you're going to run into problems and then you kind of go back to the drawing board a little bit. I would fully expect to do that in both your homework problems and your retrosynthesis, which again, will look very similar. So I would recommend working on those together in the next couple of days. So what do we need to put on first? Yeah, this big old carbon chain. Okay, so tell me why this won't work. Exactly. So alkylation won't work because you've got a primary, a carbon right there that is just a CH2. So what do we need to do instead? How do we get this long chain right here, the straight chain? So your reaction is going to be 3 steps. There's a lot of stuff going on here. So the deal is, we can rewind a little bit here. If we want to attach a carbon chain that has multiple substituents on that first carbon, we can use alkylation. So we just attach that chunk with the chlorine and it just goes on directly that way. But if we want to have a chain that's like CH2 followed by anything else, so it doesn't need to be a straight chain, but it needs to start off that way. You can't do alkylation because it would rearrange. So what we have to do is acylation first and then reduce it down. And that's going to be true of this one as well. If you want to have kind of this, what looks like a long chain, I'll erase that part up there. You want to have that long chain, you can't just attach this thing as an alkyl group because it would rearrange. So instead, we need to do acylation followed by reduction. And that's true for this one as well. We can't just attach this thing. If we looked at it and we drew out what would happen if we put these things together, it looks like we'd be good because we'd have this thing, but that's a primary carbocation. Its neighbor is secondary, so it wouldn't actually give you this. You have the plus charge right there, and then it would look very different. So in order to make this reaction happen, what do I need to do first? It's close to this. Yes. So just to be clear, you knew what you were talking about when you said that. We've said this a couple times. This is not a ketone with a chlorine on it. This is an acid chloride or an acyl chloride. So its own functional group. Kind of in the same way that a carboxylic acid is not just a ketone plus an alcohol. So this thing right here, but a carbonyl with a chlorine next door is true. So this would react. And it wouldn't give us this. It would give us, we're going to squish a lot of things in here, and I'm sorry for that. It would give us that. Okay. Now what? Yeah, perfect. So we can do our mercury. Oh, I went the other way around. Sorry. It's zinc with mercury instead of mercury with zinc. But HCl. Oh my gosh. All right, and that would turn it into. Okay, good. And then what? Perfect. So now we can put the nitro group on. Step 3, HNO3 and H2SO4. Okay. Any questions on that? So that is a lot of steps. That's how we would have to do it. Are you ready? So here's my last problem kind of in what the quiz will look like, Spain. So this is pretty close to that one.
Yeah.
So what's different?
It's meta-direct.
Yeah.
Carbon chain instead of para.
So why don't you just put the nitro on first, since that's meta-direct?
Yeah.
It's deactivated. Right. So this is a bit of a puzzle.
Yeah.
Do you see how we can solve it?
Cool.
Okay, tell me.
So we're starting off with the same one, the chlorine alpha fluoride.
Yep, acyl chloride
Acyl chloride.
or acid chloride. Yep. Okay, good. So that would give us this.
So then instead of adding the zinc and mercury, you add the HNO3, H2SO4 first.
Perfect. Yes. So at this point, if we were to go ahead and immediately do the reduction, we would end up with an orthoperic directing group, which works great in the one above that Mackenzie just did because we wanted our nitro to go ortho or para. But if we want a nitro to go meta, this is currently a meta directing group. So now we can go, no one said you had to do acylation and reduction right after each other. It's just what works to give you an alpha group. But yes, so this would give us so ZN, wait, no, you're doing the nitro, right? What'd you say you're doing the second step?
Oh, the HNO3, H2SO4.
Great. So that would put the nitro on meta because we had a meta directing group. Fantastic. All right, now what?
Then just finish the zinc mercury and hydrochloric acid.
Okay, it sounds good. So this is like, I'm going deep on the problem here. This is, some might say sadistic. Do you remember that nitro is a thing that we could reduce down to an amine? You might not remember that. It's okay. It's been a while. It's been a couple weeks. We can reduce a nitro, which is NO2, down to an NH2. There were like 4 different things that we could reduce down to an NH2. Unfortunately, the reagent that would turn a nitro into an NH2, there were a couple of them. One was hydrogen and platinum. The other one was zinc, mercury, and HCl. So this is beyond what I would expect of anybody to do on this, but maybe on retrosynthesis, just be a little careful. Also note that you can turn a nitro into an amine. That's a thing that is on retrosynthesis. So we would have to use the other way of reducing this thing. You better remember the other way of turning a C double bond O into a CH2. It's okay if you don't. Nope. So this is called Wolff-Kishner. It was the other way of doing this. We have one with an acid and one with a base. It was NH2, NH2, followed by KOH and heat. And so the deal is that this stuff would not change my nitro into an amine, but it would turn your C double bond O into a CH3. So that's how we'd have to approach this one. So good news, Gabe, you got 4 steps. Okay. So again, I put a lot of things on here. This is a little bit above and beyond what I would expect anybody to be able to do, but the ones above this, I hope that that makes sense. Do you guys feel good / better about all of this different types of questions? I tried to kind of include everything in here, but primarily what you need to focus on is electrophilic aromatic substitution with this alkyl chloride with AlCl3. And it's got a couple different things you need to worry about. First off, that Friedel-Crafts alkylation, the thing from Friday, will not work if there's a deactivating group. And it might rearrange. Two reactions for today were acylation, which won't work if you have a deactivating group. And sometimes we need to reduce it afterwards if we want to make an alpha group like that. Go ahead.
That reaction also could be one of those like enzyme reactions.
It could, yes. So wait, for this one? So there's no part of this where we're doing a nucleophilic aromatic substitution. So the one that goes at 350, that's the one that kicks off the leaving.
I do like a leaving group or something.
Yes,
Okay.
yes. So here, I can make an example of that one for you if you like. I didn't put any of these up there, but if I've got like this thing right here, and I want to turn it into into this. Natalie, what reagent would I add? So this was not on, there's not, this is, I just made this one up, but what are we doing here? What are we changing? Right, so this is a nucleophilic aromatic substitution. So what do I need to add? Yeah. Oh, whatever, right, that chunk with a negative charge. So the nucleophilic aromatic substitution ones tend to be a lot more simpler for this style of question because really you're kicking off the leaving group and replacing it with the nucleophile. So whatever ends up attached, you add that with a negative charge. And does that make sense? So that's the way that we would do this. Technically, since you asked, Colette, if I wanted to turn this into this, because there is no electron withdrawing group there, I'd have to heat it up to 350 degrees. And practically, I've never done that. I don't know that, I don't think we have the equipment to do that. That's insane. And so we wouldn't, I'm not gonna ask you that question.
So the
but
first reaction could occur at reflux with that one
Yeah.
currently.
this one with, this is an example of one of those weird Benzyme ones that I mentioned that I'm not gonna ever ask you about. But you would need to have 350 degrees to make this work unless you have that leaving group, that ortho para electron withdrawing group. You're welcome. So that's how that craziness fits in. Okay, so do you guys have any questions about this? Do you feel like you know what you need to practice, what you need to do? I know that, I just asked you 2 questions. Let's start with the first one. How are we feeling about this? Okay. You want to practice some more problems? Okay. I've got some super cool biochemistry that I would love to get through, but we could probably do this in the last 5 minutes or so. So we can practice some more problems and we'll just keep working on this. All right, so I'm gonna stop share and we're gonna go ahead and do a whiteboard. Riddle-doo. All right, what would you prefer? Kind of starting material and reagent or fill in the reagent? You guys can choose. A little bit of both. A little bit of both? All right. Let's start off with benzene. And let's go ahead and do let's do this thing. I'm gonna go multi-step here just for funsies. All right, so just to identify kind of what these are really quickly, what is this first step? What reaction is that, Colette?
the alcohol.
Yeah, so this is the alkylation, it's gonna attach an alkyl group. All right, so what should we do? Yep.
And then you're gonna do the hydride shift all the way down to the tertiary.
So with a hydride shift, it can only ever go one carbon.
Oh, never mind, then I'll go to the second.
Good. All right. So this would give us a primary carbocation, but we've seen enough examples already that you're wise to that. It would rearrange and give you that as a carbocation. So the deal with the rearrangement is that it doesn't just like happen sequentially. Otherwise, it would just keep popping and keep popping. But it has to happen simultaneously or not at all. And that's why the hydride is shifting at the same time. And it can only shift from a neighbor. So we only ever move that positive charge over one spot. And I'm glad that we talked about that. All right, so that's going to be your electrophile. And what are you going to take off of your ring? Okay, and does it matter where we put this? Where do you want to put it?
I'm gonna put it at the bottom.
Great. So we will have it attached at this carbon right here. So it's going to look a little weird. I'm going to basically turn it upside down. But this is what it would look like. It would be kind of a 4-carbon chain attached to carbon number 2 with a methyl coming off of 3. So here's your 4-carbon chain attached to carbon number 2 with methyl coming off of number 3. With weirdly shaped things like that, it can be really helpful to number it just so that we know where things are. So if I number that 1, 2, 3, 4 with the methyl on 2, the new connection at 3, then it matches here. I've got a methyl at number 2 and a new connection at number 3. Okay, so step 2, iodine and nitric acid.
So, because it's an R group already, it's ortho and para.
Yep,
So the iodine is one iodine is gonna match at the ortho, and then you're gonna have the secondary molecule.
perfect. So yeah, so this is a lot like what we did last week on our quiz. If you have an ortho para directing group, and then you do electrophilic aromatic substitution, you will get both the ortho product and the para product, so you need to draw both. So after step 2, I would still have that R group, but I would get an iodine ortho, and I would have the same thing with an iodine para. So those would be my 2 correct answers to this question. Good job. Any questions on that? All right, hearing none, moving on. Deanna, I'm going to give you some similar stuff. So instead of starting off with the alkyl halide, we're going to use an acyl halide. Then we will do so you should know all 5 of those electrophilic aromatic substitution reagents from last week. I can guarantee you that some of them will pop up on this quiz too. All right, so this is going to be also 2 steps. And I know you guys need a second to write things down. When you're ready, tell me what would happen in step 1. Yep. Okay, so this is acylation with the carbonyl. It never rearranges. Correct. Correct. So this all just attaches to the benzene ring exactly how it is. The reason that it doesn't rearrange is because the C+ can actually be stabilized through resonance with that oxygen. It's really weird, but it gives you a triple bond here, but it's still an O+, which is more stable. So whether or not you know the reasoning, it's pretty stable where it is. So that's why it never rearranges. So these guys are just, you're literally attaching it at the carbon with the chlorine, and you don't have to worry about rearranging. We can put this anywhere on the ring that we want to. Where do you want it to go? Put it on the top. Fantastic. All right, I turned this one a little bit sideways, sorry, but we're attaching at the carbon that had the chlorine. And it's a 4-carbon chain with your carbonyl at number 1 on both of them, and your methyl at number 3 on both of them. So this is the chunk that was attached to a chlorine, and now it's just attached to a benzene. All right, that sound good? Okay, so second step is SO3 and H2SO4. So what does that add on? No, this is SO3. It's okay. Anybody remember what that puts on there? This is your electrophile, the SO3. You're gonna SO3 with an H. So it's gonna attach your SO3 with one more hydrogen. So whenever we do sulfonation, this is what you get attached to the benzene. Again, we took a quiz on that last Wednesday, but count on those 5 reagent sets for iodine, chlorine, bromine, nitro, and sulfonyl to appear on here, and you won't be disappointed. All right, so where would this go though? Yes, perfect. So this thing right here is meta-directing. This chunk that we did just a second ago, that's an R group, so it's ortho-para-directing. All right, so meta-directing means we're going to go here or here, and you can choose, it doesn't matter which one. What'd you say, right side? Great. All right, so we will have this guy on there first, and then we'll have an SO3H right there at the meta spot. And when you have meta products, you don't have to draw 2 of them because it's just meta. When you have ortho and para, you need to draw ortho and para. But with meta, it's just meta. All right. Questions on that one? Yes. We did not, the one with the nitrogen, the N+. No, so that's the one that bleeds into that crazy biochem question. And it's okay. I would love to get through all of that, but if we don't get to, I consider that to be super fun extra information.
Okay, so
If you
that
guys
stuff's
would
not
rather
like
practice, we can practice. Yeah, that won't be. If you would rather practice things, I completely respect that, and that is good. All right. We'll try to do that in 5 minutes if we can. All right, Mackenzie, you ready? All right, I'm going to try to come up with one off the top of my head. It's going to be long, I'm sorry. All right, so let's do Cl2, AlCl3, followed by HNO3, H2SO4. We'll just do a para, followed by NaCN. You get 3 steps. I know you're up for it. Good news, just do one at a time and it's gonna be a lot easier. Don't try to do it all at once.
So first we just add up one.
Great, where do you want it to go? Okay, so this is electrophilic aromatic substitution. We've done this one last week. You're taking off a hydrogen and putting on chlorine. Perfect. All right, step 2. Close? So HNO3 is the reagent. What we're going to add onto the ring is a nitro group, which is NO2. All right, so chlorine directs this guy to go where? It is ortho-para. So let's just go ahead and do it para, but you would get both ortho and para. That's my little P there. So after step 2, we would put that nitro group on either of those spots, but we'll just say that we're going to do this one for it. All right, so this is NaCN. What's NaCN? Like, where are there going to be charges in this thing? The Na is, yeah, so this carbon is, yeah. So this is sodium cyanide, don't play with this, but it is a C minus, which is a strong, anytime you got a negative charge. Yeah, so that right there is a nucleophile. And so in this case, we should be looking for nucleophilic aromatic substitution. So when you have a strong nucleophile, you're doing nucleophilic aromatic substitution. And if you're doing nucleophilic aromatic substitution, you need four things. First one's a nucleophile. What's the second one? It doesn't matter if you remember the order, you just need all four. I'll give you a hint. It's nucleophilic aromatic substitution. So you need a nucleophile and great, and we got that. And it always happens at a spot where you can bring the nucleophile in and kick off perfect. So that's the third thing. Do we have a leaving group? Where? Chlorine, good. And then there's that fourth thing that we need to have on the ring. You remember what that was? Yep, an electron withdrawing group or a, yep, where? Relative to where the leaving group is, you need it to be, yep, ortho or para. And where is it now? Para. So what are we going to do? Perfect, yes. So we would, this nucleophile would come in here. So this is the reason, I don't know, you guys can do this without knowing the reason probably, but it doesn't just do SN2 because you can't do that to a carbon with a double bond. But what it would do is it would give us this intermediate where you had a C minus because you're pushing electrons into the ring. And the C minus is stabilized with an electron withdrawing group because you have too many electrons. What you need is someone to help pull them away. That's why we need an electron withdrawing group, and it has to be ortho or para to where you do this reaction. That being said, it just swings back out again and kicks the chlorine off. Remix your double bond. So really all of that stuff in the ring, it's how it happens, but practically you're just bringing your nucleophile in and kicking the leaving group off at the end of the day. And so we would replace the chlorine with what? Perfect. So we attached a nitrile at the carbon because the carbon's the part with the negative.
So you said that it just has to be an aromatic ring, so any other thing other than a benzene that's aromatic would work.
And that's true for all of these reactions. We tend to stick to benzene to kind of keep it simple for the fact that you are learning these for the first time, but they all work with other rings as well. So let's just do that third question. We're not going to get to the last page on that bridge, but I'll just show you how that works because that is totally what you were just asking about. All right, so in this case, we kind of see that happen where your OH minus, which is your nucleophile, this is not benzene, because notice I've got that nitrogen there. So what happens is you kick those electrons over. This ends up being a mechanism very similar to the acid chloride where nucleophile comes in, kicks electrons up, they come back down and kick the leaving group off. It was like that slingshot mechanism we did with acid chlorides. But the intermediates would look like this. We would have one where the Cl and the OH are attached at those spots, and we would have a negative charge here. And then through resonance, we would move it over. And here's the one that really matters. One of our resonance structures ends up actually being neutral. And so there is another resonance structure, but this is the really important one. Through all of our nucleophilic aromatic substitution reactions, and you can copy this down if you want to, you don't have to. I'm not going to ask you to draw these resonance structures. But with nucleophilic aromatic substitution, because a nucleophile comes in with a negative charge, you're going to end up with a negative charge somewhere in the ring. But if you start off with this guy in your ring, you don't actually end up with a negative charge in one of your resonance structures because the nitrogen was positive. And if you give it extra electrons, it becomes neutral. And so doing nucleophilic aromatic substitution on a protonated pyridine will be way easier than doing it on a benzene. Because with a benzene, you're always stabilizing a C minus, and it's never that stable. The best we can do is having an electron withdrawing group, ortho or para. But in this case, you actually end up with a resonance structure that's completely neutral, which is quite stable. The only reason that it would keep going is because while this is neutral, it's not aromatic anymore. So what would happen is, and there would be another resonance structure, but in the interest of time, I'm not going to draw it. You would swing those electrons back and then kick the leaving group off. That's how you would get to your product. And so there is one more resonance structure. I'm not going to draw it. And then your product would be, at the end of the day, we are going to kick off the chlorine and replace it with OH. So notice that overall, all we did is nucleophilic aromatic substitution. Your nucleophile comes in and kicks off your leaving. That's how the product works. So this is big into this molecule. This is NAD+. And so the way that NAD+ and NADH works in your body, it's one of your two big like energy molecules with ATP. It works through nucleophilic aromatic substitution. If you want to know more about that, it is never going to be on a quiz, but I'm happy to talk to you about it because I super geek out over bioorganic mechanisms. So please let me know if you want to know. Otherwise, it's okay. It can be something you ask Dr. Moore about in biochemistry. All right, any questions on this stuff? Please practice this. You can do it. We have a quiz on Wednesday. As a reminder, we don't have lab today or tomorrow. So enjoy. Thanks. Have a lovely day. It's beautiful outside.